right, if not, uh, if not even your right being better by the convention earlier of up is positive. But I thought I worded it to where we were lowering it. So, because I gave you the example of the elevator, right? So, okay. But yes, both answers are correct. I like mine better, but yours is just as right. All right. So let's look at it real quickly. You want to treat it as one object or two? One, this is an ideal candidate for one, right? Because, again, there's no friction or mass in the pulley, no mass in the string, and so it's an ideal situation to treat it like one mass that's being pulled in one direction by mg, where m is 25 kilograms, so 25 g's, and being pulled in the opposite direction of mg. So then the F-net statement becomes 25 g's minus mg, if we assume this direction to be positive. And here's where a few of you start to slip up first. Caught yourself maybe. What's the F-net equal? 25 plus m, that quantity A. Right? If I'm going to treat it as one mass, I got to take the total mass. Equals 25g minus mg. And now I'm going to, I know that A is 6, that's given in the problem. And so now I'm going to get rid of my g's and distribute the 6. And so I get 150 plus 6m's equals 250 minus 10g. Excuse me, 10m. Right? That was just arithmetic. Now I combine like terms. I get 16m's equals 100. Therefore, m is 100 over 16, which is 6.25 kilograms.
How'd you get the 250 minus 10 again?
I just multiplied. I just got rid of the g by doing 25 times 10 and m times 10.
Oh,
Okay? Make sense? So, see, even this, which was a harder Atwood machine question, you can do, right? So now let's step it up a notch. Let's place a block of 5m on a table connected with a massless string to a mass of 2m. And at first, we're going to make the surface frictionless. At first, yes. You know that we're going to ramp it up eventually. And literally, eventually. So I would love to know at what rate the 2m block accelerates downward in this problem. So let's walk through it. First of all, I've got the same options. I've got the same options as I did for the Atwoods, right? I can treat it as one system, or one object, or a two-object system. Which do you want to do? One? Okay. If it's truly a one-object system, it has a mass of 7m. And what forces is our 7m mass, or our 7m system experiencing? Okay.
You mean left, right?
Okay. Yeah, so let's, before we combine it, let's go back and look at forces. Let's just draw free body diagrams on these two masses before we combine them. What are the real forces on the 5M?
mg.
Yeah, mg down,
So that'd be 5 mg.
which is 5 mgs, yeah. And normal up. And then tension to the right. What about the 2M?
2 mg.
2 mg down and tension up. Okay?
Which couldn't we know is 2 mg because tension would be equal to.
Yes. So the tensions, if I was treating it as a two mass system, the tensions would be equal, and so I'd set them equal to each other. If I treat it as a one mass system, then it's internal, and so tension I can ignore entirely. So then what does the force diagram look like for the 7M total block? Well, well, no. Because thanks to the pulley, what's true about the 5 mg and the 2 mg? Thanks to what the pulley's doing, the 5 mg and the 2 mg forces are in the same direction, in opposite directions.
The same direction.
Huh?
The same direction.
What'd you say first? You said something under your breath. Yeah. What does mixed baiting have to do with it?
One's going down, one's going to the right.
Yes, they are perpendicular. And that's where we got into our whole mixed baiting argument, right? If they're perpendicular, then they're independent of each other. So thanks to the pulley, the 5 mg and the 2 mg are now perpendicular, and so I have to make sure I show that so that they don't affect each other.
On the 5M pulling to the right and not mg.
As an individual object, yes. But when I combine the two objects, then tensions cancel.
But the 5 mg is still going down, not to the right.
What? Well, okay. Which are you talking about? As one mass or two masses?
I don't understand how you can change the 5 mg going down from the two masses to it going perpendicular in the one mass.
Oh, I'm actually not. I'm going to call down 5 mg.
Okay.
But which direction is the 2 mg then? To the right.
But both mg's in the two mass picture pull down. How do you?
Yes, but this pulley changes the direction of one of them. Just like in the Atwood machine,
But it changed the direction of
it
tension,
changed
not mg.
the direction of both.
I know it's
But
going
mg
fast,
is
but
in line with tension. It's collinear, or anti-parallel.
But it's not collinear in that other mass.
Yes, it is.
Their tension is pulling.
Tension
to the right.
and mg are still along the same line.
5 mg is going down, but tension's going to the right.
Right, for that one, but I'm talking about for the 2 mg.
Okay.
This pulley takes that downward force and makes it a rightward force.
Okay.
Right? And so I'm just drawing it on the one mass system, I'm just drawing the 2 mg as being the rightward force, which is what the pulley made it do.
Okay.
Okay? Yes. They have to stay perpendicular, yes.
So it doesn't matter which way you draw them as long as they're perpendicular.
Exactly. I mean, I can orient, it's just like my coordinate system. I can orient it however I want, so long as I'm consistent. This just makes the most sense to me, because I picture that 5M mass sliding across the table.
You just shattered like 12 units of mass.
That's pretty much all.
I just love it when that happens.
Breaking all the rules.
So what else we have?
Making our own coordinate planes and stuff.
What other forces?
Normal?
Yeah, just normal, right? Come on.
And that'd be equal to 5 mg, right?
What's that equal to?
5
Yeah, it's equal to 5 mg because that 5 mg is not going to accelerate vertically off the table.
That's good.
But I don't need that right now, so I just call it n still. N. Alright? So now, as you just alluded to, we've got two fnet statements. Let's take fnet y, since it doesn't matter. Fnet y is
N minus 5 mg.
n minus 5 mg, and it's 0, because it's not going to accelerate off the table.
So N equals 5 mg.
So n equals 5 mg, which again, isn't relevant now, but it's going to in just a second. And then fnet x
2
equals 2 mg. And yeah, we need to define positive. Right is positive, so it's positive 2 mg. Fair enough. So now all we have to do is find out what A is. Fnet equals 7 MA, right? Because who's accelerating? All of it. All 7 M's are accelerating. So when I get ready to do my Fnet statement, I need the total mass of the system. Equal 2 mg. Now the M's cancel. And A is 2/7 of G, which is what, 2.7-ish?
Yeah, 2.85714.
We'll call it 2.9 meters per second squared. That's how fast
That's going
which
into
mass is accelerating?
The whole thing.
Yeah, the whole thing. The 2m and the 5m are
so
both
if you
accelerating
apply
too.
to that problem, the 5m is going to the right, and the 2m is going down.
You got it.
How did we know the 2m was going down? Just because we knew the 5m was going to the right?
Well, or just conceptually, what direction could it go? Are there any forces that are causing the 2m mass to go up or the F5m mass to go left? No, so our only option is down and right. Without friction, yeah. Okay? So, let's go ahead and just append this a little bit for a little practice. Let's say that the 2m mass started off 0.4 meters above the ground, and you can assume that there's plenty of string. If that's true, then how far away from the table will the 5m mass land?
Say what?
If the 2m mass started 0.4 meters above the ground, how far away from the edge of the table will the 5m mass land, assuming there's plenty of string?
We need to find the amount of time it takes for the 2m to fall.
Exactly.
And apply that to the acceleration of the 5m going out due to inertia.
Yes.
Wait.
Well, yes, except for the due to inertia part, yes.
Right.
So,
Like
we're going to
saying it
find out,
flies off the head.
yes,
Okay.
we're going to find out how long it takes the 2m mass to accelerate down to the floor. And then, yes, apply that to how much the 5m mass is going to accelerate along the table. And, oh, by the way, I do need to tell you the height of the table. The height of the table is 1.1 meters. Alright? So let's do that. First of all, we said we got to have the time that it takes the 2m mass to hit the floor. Okay? So let me just move this out of our way, since we know the answer now. So the time to hit the floor. What equation am I going to use for that?
1/2
Yes, delta y equals initial vertical velocity times time plus 1/2 the vertical acceleration times time squared. What was the initial vertical velocity? 0, right? And so now delta y is 1/2 at squared. Solve for t, and you get t is 2 delta y's over a square root of that quantity, which is 2 times 0.4 over, what's a?
2.9.
Good, 2.9. Careful not to make it 10 because we're not free falling, right? We're tied to a string to that 5m mass up on the table. So he's slowing us down. And so how long does it take for the little block to hit the floor? 0.5 seconds, we'll call it.
How much string is in between the 5m block and
Plenty.
this table? Well, if it's plenty, then it will just get pulled along, won't it? It won't actually come off. In between 2m and 5m, then depending how far 5m is sent back on the table, like it could just like go like that and never make it to the edge.
Really? Who sees the problem there?
The pollution in play? No, the string is made of light, so it's irrelevant, Jacob.
No, that's not what he's asking. Repeat what you said.
Like, if like the 5m is like way out here, and the 2m's right here, when the 2m falls, the 5m may not make it to the edge of the table.
It does. Jacob, it's frictionless.
Therefore,
They keep on going, and until the edges of the table.
yes.
There's nothing
Yeah,
to stop
you can have an 300 meter long table. As long as we spend 0.5 seconds accelerating that 5m mass, as long as it's frictionless, guess what that 5m mass is going to do?
So does it keep accelerating after that 0.5 seconds, or does it just start going up?
You tell me.
Well, if there's nothing that's going to keep accelerating it, it's just going to keep going on its own.
Right. So once it's done with this 0.5 seconds of accelerating, it won't accelerate anymore either way. So it'll go that constant velocity all the way until the end of the
You have to
table.
figure out how far it goes when it accelerates and how far it goes at constant velocity.
No. All I care about is what are we after? If we're going to find out how far away from the edge of the table it lands, what do we really need to know about it?
Delta X.
How long is
Well, yeah, I mean on the ground, but
how long is it in the air?
how long it's in the air and
Yeah.
how fast it was going when it left the table. Those are the only two things you got to know, right? And what we're trying to find now is how fast it was going when it left the table. And if it's a frictionless surface, it could have started back 3 miles, accelerated up to, in this case, 1.45 meters per second. And then guess how fast it's going to be going when it gets to the edge of the table?
Still 1.45.
1.45.
Like, did it
What if it started off like right here, and then it got pulled off, but the full 0.5 seconds of acceleration never happened, and then it starts free falling?
Right.
That's a different force.
Absolutely, and that's why I said there's plenty of string.
Oh, so it's far back.
Yeah, it's far enough back that
It
it will finish accelerating before it hits the edge. Yeah. Okay, so we just did the second part, right? Which is how fast is it going to go? Well, the 5m mass started at rest, and it accelerated at 2.9 meters per second squared for half a second. And so the big block, and the small block for that matter, right, because they're tied together, when the 2m block hits the floor, they are going 1.45 meters per second. And that then becomes the launch velocity of the 5m block when it does eventually hit the edge of the table, right? And so now we've got a problem from last year. We've got an object going 1.45 meters per second, launching horizontally from a height of 1.1 meters. Can you find out the range, the horizontal range? You better know how to, right?
Now the acceleration y is 10, isn't it? So the 2
Yes.
on the ground.
Yes.
Or
Now,
that the 2 is on the ground, right?
right.
So it has to be even more string.
Well, yes, that's why there's an adequate amount of string. Yes. Alright, so I'm going to find the time it's in the air using vertical. Come on. Now, what was the initial vertical velocity of the 5M block? Yeah, 0. So by the same algebra we just did, the time is 2 times delta y, which is 1.1, over g, which in this case, right, it is accelerating 10 meters per second now because it's the 2m mass is basically out of the way now. It's just a 5m mass free falling. And so who is that? 0.47 seconds. And then I use my horizontal. And in this case, is anything 0 in this equation? Yeah. The horizontal acceleration is 0, right? Because there's no net force acting in the horizontal direction. Therefore, I take my 1.45, which was a horizontal velocity, times the 0.47 seconds that it falls, and I find that it ends up 0.68 meters. That's what I did. If I divide both sides by t, that's all that came from.
You didn't need the 1/2 at squared and all that
But
stuff.
Jacob, this is the root of the formula. You always have to write the root of the formula on income digits, because then if you do something wrong, they give you credit.
Yeah, always show where you started. And you started
That
with
was the formula. Velocity equals delta x over t.
average velocity is delta x over t.
We have the average velocity, and
How do you know we have the average velocity?
Velocity, Jacob, not the average.
The only way you know you have the average, no, seriously, the only way you know you have the average is if the acceleration is 0. And so this step shows them that I know that the reason that's average is because the acceleration is 0. Okay?
Can't wait till we all fail the physics exam and just finish the world. That will be
somebody's
so
wrong.
quick.
All right.
Can't
All right. So now let's step it up yet another notch.
I'm looking way ahead, guys. Yes, I'm looking forward to that. I'm looking forward to being old. That's what people say.
with your cane and whatnot.
Yes, exactly. Hobble after the neck.
Dr. Steam, you just come up with these math problems.
Usually.
Oh, that's not M, that's mu. No.
All right. So now we have a 1M block suspended from a light string draped over a massless and frictionless pulley connected to a 3M mass that just happens to be suspended on a surface with which it has a static mu of 0.4 and a kinetic mu of 0.3.
The sad part is we know it's going to be more than the static mu, because otherwise it wouldn't be that problem.
Well,
He just kind of
if he's just making it up, then
But then we'll get another one that fits the definition.
well, sure. Then we'll
Two problems.
exactly. We're going to work it both ways, and so you can't assume which way it is first, right?
Sure.
So does the small block accelerate? And if so, at what rate? Alright, so as we were just saying, in order to find out if it's accelerating, we're going to look at the force diagram, which if you do a combined system of 4m, there's a normal force up, a 3mg force down, an mg force to the right, which was down but the pulley made it right, and fric to the left. And we're eventually going to, well, no, let's do it now. So F net Y is what? N minus 3mg. And since it's not accelerating vertically, N equals 3mg. Right? And then F net X equals mg minus fric. Well, what are the conditions we're looking for? We want to know if the small block accelerates. We want to know, hey, is F net X greater than 0? In order for F net X to be greater than 0, then if F net X is greater than 0, then which is bigger, mg or F? Then mg is greater than fric. So I want to know, is mg greater than fric? Well, what is fric? Fric is mu static normal. Well, what is mu normal? Well, normal is 3mg. So mu static mg. Stupid pen. It's getting tired. Bless you.
Just mg or 3mg?
Yes, 3mg. Come on. My pen.
Dang it, that means I'm getting sick.
You guys are going to...
Okay. So that's 3mg. My pen. There we go. 3mg.
32 is going to be the healthy one for quarantine.
So what is mu static times,
I see.
what's mu static times 3?
1.2.
1.2. So is 1 greater than 1.2? No, not recently. I just divided both sides by mg. So 1 is not greater than 1.2, therefore it's not accelerating. And then the follow-up question I just told Jake to go ahead and start on is, how does this question change if it's a 2m block? Okay. So go ahead and find the rate it accelerates if it's a 2m block.